Dear students, in this session, we will discuss about isomerism. In earlier session, we discussed about isomerism. Organic compounds will be having same molecular formula, but different structural formula, different structure are called structural isomers, what we discussed in earlier. Okay, chain isomers, positional isomers, metamers. Okay, and those are the things we discussed in earlier session. In this session, we'll be discussing about the stereoisomerism. Organic compound will be having same molecular formula and also having same structural formula. Both structure as well as molecular formula will be same. Then what is the difference between them? Their spatial arrangement. Their spatial arrangement is different. So organic compounds will be having same molecular formula, same structural formula, but differ in their spatial arrangement of the group of atoms attached to the organic compounds or for the compounds. These are called as stereoisomers. Stereoisomers divided into two types. So first one is geometrical isomerism. Stereoisomerism divided into two types. First one is geometrical isomerism. Second one is optical isomerism. So we need to study about the geometrical isomerism in detail in this chapter. In next chapter, we'll be discussing about the conformations. Okay, how the variations, how the geometrical variation like Saha structure, Newman projection, skew and Gucci's conformations. Okay, now geometrical. What is the difference between geometrical isomerism and optical isomerism? So geometrical isomerism is a phenomenon. Okay, so the organic compound which have a same structural formula, but differ in their spatial arrangement, of an atoms or a group of atoms about the double bonded compounds. These are called geometrical isomers. This phenomena is known as geometrical isomerism. So these isomerism exist by means should be what are the condition? Which are the isomers? Which are the compound shows geometrical isomerism? What is the condition for this? This isomerism, which have a same atom or groups, lie in the same side. Okay, same side. So this geometrical isomerism divided into means identified as two types. One is cis isomerism and the second one is trans isomerism. Cis and trans isomerism. So we'll see what is the meaning of cis isomer and trans isomer. So what is geometrical isomerism? So a compound which have the same structural formula but differ in the spatial arrangement of atoms or a group of atoms about the double bonded are called geometrical isomers. This phenomena is known as geometrical isomerism. So in that compound, based on that the group of attached group on the same side or opposite side, we can classify it as cis isomer and trans isomer. We'll see that. Next, optical isomers. So we know that optics, light. So when normal light passes through the polarimeter, when normal light passes through a polarimeter, then what happens? Then the polarimeter filters the all directional light into the one direction, unidirection. Then the light is polarized. If the light is polarized, there is a light in all the direction of the passing with polarimeter. So we'll be getting the direction means unidirectional light. Okay, in same direction. Then it is passed through the solution means organic solutions. If this organic solution can able to rotate the plane polarized light towards the right or towards the left. So if the organic compound can able to rotate the plane polarized light towards the right, then it is called dextrorotatory. Dextrorotatory. So this one is represented with the D configurations, okay, with the representation of the dextrorotation. Dextrorotation means organic compound can able to rotate the plane polarized light towards the right side, then it is dextro. And if the organic compound can able to rotate the plane polarized light towards the left anti-clockwise, then it is called levorotatory. Levo is represented with a small letter L. Dextrorotatory and levorotatory optical isomers. So the plane polarized light passes through a prism, passes through an organic solution. If the organic solution can able to rotate the plane polarized light towards the right, then it is called dextrorotatory. If the compound can able to rotate the plane polarized light towards the left, then it is called levorotatory, then which is represented with D and L configurations. What are the condition for what are the condition for shows optical activity? To show optical activity, the carbon means organic compound must be a chiral carbon. Chiral carbon is one which carbon group or the group attached to carbon must be a different group. Example, one is hydrogen, another is methyl, another is ethyl, another is chloride. Then all the four different groups are attached to this carbon, then it is called chiral carbon. Chiral carbon. So first condition to show optical activity, carbon must be the chiral carbon. Second one, this should be non-superimposables, non-superimposable on their mirror images. So organic compound must be mirror image, non-superimposable on their mirror images. What is the meaning of non-superimposable? What is the meaning of non-superimposable? So we know that the mirror image, the compounds of the mirror image. Example, if you consider simple compound like CHH, here OH, H, H, okay, and H, CH3OH. This is a mirror image of OH, right side, no, here OH is right side, left side, carbon, hydrogen, hydrogen, hydrogen. So this is not superimposable. We cannot keep the same group on the same side. If we place carbon one above the other, then hydrogen will be in right side and hydroxyl group will be in left side in this group one. So structure one and structure two. If we keep one carbon on the other carbon in one side, the first structure OH will be in right side, in second structure OH will be in the left side. So these two are the mirror images, but these are non-superimposable, non-superimposable. So difference between superimposable and non-superimposable. If you take an example of the methane compound, okay, if you take an example of methane, that is the mirror image, right? So carbon, hydrogen, hydrogen, and here, so carbon, here hydrogen, 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 and hydrogen. So what will be, so this will be the mirror image, no? So from here also, hydrogen, hydrogen, hydrogen. Methane is mirror image of, because same position, when we place one carbon on the other, so hydrogen we place in same hydrogen, means there is no difference. So this is superimposable on their mirror image, but this is non-superimposable, non-superimposable on their mirror images. So later on in second chapter in hydrocarbon, we'll be studying in detail about optical activity. So what is an optical isomers? Organic compound can able to rotate, means they'll be having same molecular formula, same structural formula. They differ in the rotation of the light, plane polarized light towards the right or towards the left. If the organic compound can able to rotate the light clockwise or right side, then it is called dextrorotatory. If the plane polarized light can able to rotate left side, then it is called levorotatory. So you need to know condition for the optical activity. It should be a chiral carbon. Carbon must be consistent, must be attached to four different group. Then it is chiral carbon. And the second one, carbon, a molecule should be non-superimposable on their mirror images. Should be a mirror image. Should be a mirror image. Should not be imposable with each other. Should be non-imposable and their mirror image. This type of compound will show optical activity. Later on, we'll be studying about this conformation and optical activity. In this chapter, in this session, we'll be discussing in detail about geometrical isomers or geometrical isomerism, complete phenomena. Okay. Now, geometrical isomers, we know that the definition of geometrical isomers. So, what are the conditions for geometrical isomers and how this will be identified? If the attached group will be having same molecular formula, same structure. Okay. Example: cis butene. Till to now, 2-butene is nothing better. So one and second, first carbon, if you consider second carbon here, any one carbon, CH3, C double bond. Okay, then here is CH3, and then hydrogen and hydrogen, right? So here in this structure, name of the compound 1, 2, 3, 4, butene. Second carbon having double bond, but2ene. Cis-but2ene. So CH3 group attaches to same side. In the same side, the CH3 group is attached, then it is called cis. Cis. So in this case, carbon, CH3 group and CH3 group will be present in same side. This will be present in same side. Trans-but2ene. So geometrical isomers, this will be identified as two types. One is cis isomer, second one is trans isomer. So trans isomer, carbon-carbon double bond. Here one carbon, CH3, methyl group, and here is methyl group, is CH3. One hydrogen is here and one hydrogen is here. Then what will be this compound? This methyl groups are opposite with each other. The two groups, these are adjacent, are same side, and this hydrogen and hydrogen are opposite. Or methyl group and methyl group, these two are opposite. If opposite, then it is called trans. Trans-but2ene. So trans-but2ene. So that is a compound. So same side, whether the compound will be consisting the same side. So why this will be changes? Because if the two bulkier group, so out of this cis and trans will be a more stable than cis. So in the cis compared to this trans is more stable. Why trans is more stable than cis? Because in the cis isomer, both the bulkier group will be in the same side. If both the bulkier group present in the same side, there will be steric endurance. Bulkier group congested. Due to that, the molecule try to move away, the adjacent group try to move away as much as possible. If the bulkier group are away with each other, then there will be less repulsive force between them, less hindrance between them. If the less of hindrance between them, then it will be more stable. Trans isomers are most stable than cis isomer. So what are the conditions for the geometrical isomers? The first one condition, the molecule must have double bond. Organic molecule must have double bond. And the second one, and these two atoms or group of atom should attach to the same carbon atom must be different. What the group attached to the group of two atoms or a group of atoms? On two atoms or a group of atoms attached to carbon must be different. Okay, then they can exhibit geometrical isomerism. Okay, so geometrical isomers. So this phenomena is called isomerism. So not only this, if you can take any compound like Higgs or pent carbon number 2, 3, 4. If you consider in that, so what happens? Steric effect greater will be influencing the structure reactivity in the organic compound. If the bulkier group, more of the group, then the steric endurance is more, then the stability will be decreases. So we'll notice that, okay, in the case of 1,2-dibromoethane, 1,2-dibromoethane, we call as cis compound as well as trans compound. In the case of the cis, carbon, carbon, this will double bond, carbon and carbon. Here, hydrogen. So I'll write here this carbon and carbon double bond with an hydrogen, and here is bromide, and here hydrogen, and here is bromide, Br. So this Br and Br, this bromide and bromide in same side, then it is cis. Okay, this is what is the name of this compound? This first carbon and second carbon. First and second carbon will be having, this is 1 and this is 2. 1, 2 dibromoethane, 1 comma 2 dibromoethane is the name of the compound. So in this, if the groups are here indifference, no. So what happened? So try to move away. If they try to move away, what will happen? So this will be carbon-carbon double bond. Here is an hydrogen. Here the bromide, Br. And here as an hydrogen, an opposite side is Br, bromide. Then the substituent group, 4 different groups are opposite with each other. If the opposite with each other, then it is called trans isomer, trans 1 comma 2 dibromoethane, 1 comma 2 dibromoethane. So this, if what happened if the carbon the same means will be not having the two attached group are not different, whether the compound which shows isomerism, no. So you need to write, I'll see, well, let's see, carbon double bond for this hydrogen, and this is hydrogen, and will be an hydrogen. All the three are different, and one is an ethyl group, CH3CH2 is called ET. I'll write an ethyl group, ET, ethyl group C2H5. So the same, if the only ethyl group is different, all these are same. Okay, if it changes this carbon position, carbon double bond, hydrogen, and here hydrogen, and in this side, if you write an ethyl group, so there is no difference, doesn't create any difference. If doesn't create any difference, then ethyl group and this ethyl group, then what will happen? So there is no geometrical isomers. It is not a geometrical isomer. Okay, so because that must be consist of 2 different groups. Not only this, we'll see 1 or 2 example in detail about geometrical isomers. So in this carbon, so carbon double bond. So for this, so butane, carbon number 4, hydrogen and COOH, carboxylic group, and here COOH, the formic acid group, HCOOH, no? So COOH, carboxylic group. So HCOOH is formic acid. So this COOH, okay, and this carboxylic group and this H group. So this will be COOH and COOH, carboxylic group present in the same side. This is cis isomer. Cis isomer. So the name of the compound is MALEIC, malic acid. MALEIC, malic acid. Malic acid, the name of compound. If this will be opposite, C, double bond C, and COOH, and here is COOH, and here is a hydrogen, and here is an hydrogen. So this will be a trans isomer. The name of the compound is fumaric, FUMARIC, fumaric acid. Fumaric acid. It is a trans, and this is a cis compound. Are you getting? Cis and trans isomers. Geometrical isomers have a different physical properties. However, their chemical properties are similar but not identical. You need to remember this point. Geometrical isomers have different physical property, but will be having the same chemical property. Their chemical property is same but not identical. Not identical. You need to remember this. Okay, so this is about geometrical isomers. So in the case of the compound, in the compound, we'll be noticing that cis and trans, what will be uh, the dipole moment, how to give the polarity, how to seize that the polarity within the compound. If this is what we studied in the dipole moment, this is what we studied in dipole moment. This is the same. I'll write the compound. No? So 1,2 dichloro ethane. 1,2 dichloroethane. If you take a compound of 1,2 dichloroethane, carbon, double bonded carbon. Here is the chloride. Okay, and here will be chloride, Cl, and hydrogen and hydrogen. 1 comma 2 dichloroethene. Ethane, not ethene, double bond. So what happened in this chloride? Here, the more electronegative, electron shift towards this carbon. From here also, electron shift towards this. So we'll be having a dipole moment. Mu is equal to 1.90 device. It shows a dipole moment, cis isomerism. Cis isomer. In the case of carbon-carbon double bond, one chloride is here and another chloride Cl is here. Okay, and what will happen to this carbon to a chloride? So it is away. Sorry, from carbon to chlorine, chlorine is more electronegative. No, it is away. From here, carbon to chlorine, it is dragging away, dragging away. From here is hydrogen and here hydrogen. What happened? So this will be drags. This will be drags the pair of electron away with each other. Away with each other, then mu is zero. Mu is zero, that is trans, hence it is most stable. Trans, it is most stable. What will happen? So equally they'll drag, no? If equally the drag, net resultant dipole moment is zero. Here this will be dragging. Here it is dragging and here it is dragging. It is an unequal one direction. So the polarity is generated in the cis, but not in trans. Are you getting? So this you can write for any of the compounds, cis and trans. And also in the case of this dipole moment, we can able to explain polarity with the help of cis and trans isomer. As well as in the case of cis isomer, we'll be having high boiling point than trans. Cis, no? Cis, in cis, polarity is generated, right? In cis isomer, polarity is generated. If polarity is generated, ions, ionic compound than non-ionic, then obviously should have an high melting point. No? If polarity, example, carbon-carbon, butane, cis butane CH3, and it is NCH3, and hydrogen as well as this hydrogen. So this is cis butane, cis butane. So compared to this means in the same side, they'll be dragging in the same side. This boiling point will be 277 Kelvin. 277 Kelvin. But in the case of carbon-carbon, this is an hydrogen, the same CH3 group, methyl group. Here in opposite CH3 group, trans butane. In this, they'll be away with each other. So away with each other, then this is a trans isomer and its boiling point will be 274 Kelvin. If 277 to 274 Kelvin, so cis isomer, okay, will be having high boiling point than trans isomer because polarity will be generated. In the case of solid, trans isomer will be having higher melting point. In the case of the solid, so trans isomer will be having high melting point. Okay, than this is. This is because of two better symmetry trans isomer with which trans solid fit very well into the crystal lattice. In crystal lattice, the trans isomers fit very neatly. So very well arrangement of the molecules very neatly, they can fit into the crystal lattice in solids. Hence, trans isomers will be having high melting point. Okay. Next, to cis and isomers as higher refractive index. Cis isomer having higher refractive index than trans isomer, and the stability of trans isomer is more than cis. Total overall stability of trans isomer is always greater than cis isomer. Always greater than cis isomer. This you need to remember. This, what we consider the geometrical isomers, this also notation represented as E and Z system of geometrical isomer. E and Z system of geometrical geometrical isomers. What is EZ system of geometrical isomers? When the there's three or four different group attached to carbon atom of a double bonded. Okay, then it becomes difficult to assign cis. Okay, how it will be? Example, four groups. No, it carbon, carbon double bond. One is bromide, another is iodide, one is chloride, and here is fluoride. Then it is very difficult to assign cis and the trans isomer, which of the compound is present in the same site or an opposite site. Then we can use E and Z system. E and Z system, E and Z notation for isomer. It was developed by Chan and Ingold. CHAN, Chan and INGOLD. Chan and Ingold. So started to notating or given rules for to write to represent E and Z system of geometrical isomers. So you need to know that it is the two words of German what we using of E and Z. These two are German. E means in German zusammen, meaning together. Zusammen. Okay, so Z is zusammen, E is entgegen. E in TE, sorry, ENTGENE, entgegen, which means together, sorry, which means opposite. Entgegen is opposite. Zusammen, ZUSAMMEN, zusammen means together. Together means same side. Together means same side. Entgegen means opposite side. So E and Z rotation. To write the E and Z notation, so that they assign that the atom with the higher atomic number, which goes more priority, higher atomic number will be getting the more priority, more priority. Example, fluorine, bromine, iodide. So more atomic mass is iodine. No, iodine is greater priority, first prior, then bromide, then chloride, and then fluoride. So priority goes to in this manner. So as well as in the more group, example, in the case of methane and ethyl group, C2H5 or etc., greater will be the carbon, greater will be the branching, that will be getting more prior. So in second chapter, we'll be discussing in detail about E and Z rotation, the same as giving of more priority. So this is about geometrical isomers. Okay, in hydrocarbon, we'll be studying in detail about geometrical isomers as well as optical isomers. Okay.